Okay, so today we are going to be starting a new unit. We are going to be starting to talking. I can't talk apparently. We are going to start talking about some of the different types of chemical reactions. So last semester we talked about the precipitation reactions and acid-base. Now we're going to be talking about some things that are a little bit more complicated. So our first unit is going to be on redox reactions. Redox reactions are interesting because they are things that we use every single day. We might not know about it, but they're important for our quality of life. Okay, so a redox reaction is a combination of two separate chemical processes that have to occur at the same time. The first of the processes is called oxidation. Oxidation is what happens when some substance loses electrons. I'm abbreviating electrons as E- in the same way that we did when we first learned about the atom in September. So oxidation is the process that's referred to when something loses an electron. If a substance is losing an electron, somebody has to be there to obtain that electron that was lost. We can't have electrons that exist just like randomly in space because electrons are always moving, and when they are moving, they can be dangerous if they're not like harnessed. And so the other process is called reduction. Reduction occurs when a substance gains electrons. So one substance will lose them, one substance will pick them up, and because those two things have to happen together, you can't have a reduction. You can't have somebody that's taking on electrons if there's not somebody there to release them to begin with. And so because these two things must happen together, that's where the name redox comes from. It's really two separate things that are happening, but they have to be happening together. And so we get the name redox from the beginnings of these two words. Why is it that it's called redox and not oxred? I don't know. But that's where this name comes from. So what's the purpose of a redox reaction? Because you are transferring electrons, you're able to do something with those electrons. To generate usable energy. So that's the whole purpose of the redox reaction, is to allow a chemical process to transfer electrons so that those electrons can be used to do something. In physics, we would call it electrical work. Well, I guess in chemistry we call it that too. But most of the time when we have a redox reaction that we're harnessing in this way, we're using it to generate electricity. What is electricity? Like in its most basic definition? Or let me rephrase that. What is current? Does anybody know what electrical current is, Mason?
The movement of electrons?
Yes. Okay, so we can use the other word for electricity, or electrical current. And we know that if you have some flow of electrical current, that what you really have is a flow of electrons. So, does anybody, Tanya has her phone in her hand. Good. No, that's okay. Like turn your screen on. Right now, her phone is doing a chemical reaction because her screen is on. So if you turn your screen on, like my tablet is recording this, my phone is here with my little lecture notes. Even your calculators, if you turn them on and it's backlit, so there must be some electricity that is moving in order to create this. What's happening? So how does that light up? How does your phone screen turn on? What's happening? Mason?
Electrical current is being generated by the battery, which then goes to the LEDs.
Yes, all those little photocells that create the picture that's on your phone. So your battery right now, well, and it's in my classroom, so it's also probably working because it's probably searching for a signal. So your battery right now is going through a chemical reaction where it is producing electrons in order to generate electrical current, to do electrical work. What happens when your battery gets to zero? Or does anybody let their battery get to zero? What percentage do you let your battery go to before you plug it in?
1.
Okay, I'm not that way. I'm like never that way. Okay, so how many of you plug your phone in when it gets to 30? 20? 15? 10? Is it more? Is it more than that? 5? Okay, so you guys let it go down pretty low. Oh, interesting. Mine got down pretty low yesterday, but I was on my phone a lot. I almost never, my battery lasts pretty much all day. Does your battery last all day? Do you have to charge it midday? Yep. Sometimes when our batteries get older. We'll talk about that. Okay, so what happens though when your battery gets dead? You have to plug it in. So the plugging in of your battery is reversing the chemical reaction that took place to power your phone in the first place. That's why your battery doesn't last forever. We'll talk about that in a couple of class days. Okay, so how can we know if any kind of reaction that we're showing is a redox reaction? And the answer is a little more complicated than I wish that it was. It's not something easy like when you look at an acid-base reaction, you know that it's acid-base because water is one of the products. That's easy to see. It's easy to see if it's a precipitation reaction. If you produced a solid from 2 aqueous solutions, that's a precipitation. Like you can just look at it. You can look at a redox reaction, but there's a little bit more figuring that has to go into play. And so what we really need to do is to identify oxidation numbers. Oxidation for every element or species, I'm going to call it, in the reaction. And then we have to decide, is the oxidation number changing? If it's not, then that substance was not oxidized or reduced. So before we start to look at like how the oxidation numbers will change, we need to know how to identify what those oxidation numbers are. So that's what we're going to spend the rest of the time today doing. I have a new colored sheet for you. It's red. In fact, the color of this paper is called, wait for it, Red Rocket. And hopefully this piece of paper will help you to identify oxidation numbers. It's not super difficult, but if you're not going to pay attention, it will be tricky. You guys kind of got to lock in.
Yes, we got that. Ooh.
Okay, so let's take a look at our red rocket paper and try to decipher what all of it is saying to us, and hopefully that will help us to know how to identify oxidation numbers. Your periodic table will be helpful to you, but only some of the time. Okay, so before we do anything else, I want you to turn over to the back side of the periodic table. So the title should say oxidation states and electronegativity. Does it also say electronegativity?
They're around beginning.
Okay. Okay, so we're going to look at the oxidation states. What is an oxidation state? An oxidation state is the same thing as the oxidation number. I use those words interchangeably, so don't get confused by my inability to be consistent. They mean the same thing. So what is the oxidation state? Basically, it is it really just is describing how the element behaves in that particular compound. If you're looking at your periodic table, you'll see that some elements have more than one oxidation state. Like, look at molybdenum. He's element number 42. He has 1, 2, 3, 4, 5 different oxidation states. That's pretty many. Look at lithium. Lithium's element number 3. Only 1. Now, what's tricky about this is that this list that I made for you on this periodic table is not all of the possibilities that an element could be. It's just the most common of them. So there are, like if you feel like you want to take AP chemistry, there are sometimes where the oxidation state is 0. There are sometimes when it's a fraction. Most of the time it's a whole number. It'll only be a whole number for you. But there are sometimes when it is a fraction. And so this is not exhaustive. This is not all of them. It's just like a start. And that's the best I can do for you. Okay, so sometimes it'll tell you what it most commonly is, but you should always be looking at the compound itself because that will give you more information than even this periodic table will. Okay, so let's take a look at the rules on your red sheet. The first rule says all elements in their free state, in other words, uncombined with other elements, have an oxidation number of 0. All right, so all elements by themselves, the oxidation number, which I'm going to abbreviate as O dot N dot, that equals 0. So some examples of that. Any of the metals exist just as themselves. So like mercury, silver, gold, they don't have little numbers because when you have a sample of them, they're not combining with each other to form a compound. So all of these oxidation numbers would be 0. The nonmetals aren't like that though. Most of the time they exist as what we call diatomic elements. Di meaning 2, atomic meaning atoms, so 2 atoms. And so Cl2, O2, H2, N2, Br2. The oxidation number here also is 0 because they're not combining with other elements, just with themselves. Some elements like sulfur do weird things, as well as phosphorus. And so it doesn't matter what that small number is in the lower right corner. If there's just one kind of element, the oxidation number is always 0. So if we were to identify any of these things, the answer would always be the same. Okay, it'll never get any easier than this. Are we feeling okay? Okay. Rule number 2. Hydrogen is always +1 except in metal hydrates where it is -1. For you, in this class, it will always be +1. Always. Always, always, and forevermore. If you take AP Chem, though, that's not true. If you take any chemistry in college, that's not true. But for us, it is. Okay, so if I were to give you this example, H2O, now here we've got that H2, but H2 isn't by itself. And so when it is bonding in a compound, the oxidation number of hydrogen here will be +1. Notice how I am writing my oxidation numbers with the charge in front of the number. Normally, I would be writing it behind. So what's the charge of oxygen from your, like the charge from your periodic table? What's the charge of oxygen? So you might want to flip it over. It's 2-. This is the charge. In order to have an ionic compound, your substance has to be charged. This is not an... Damn it. Sorry, hang on. I really am not this technologically challenged. I just don't know how to use this thing. This is not an ionic compound. So this hydrogen really doesn't have a +1 charge. That's because this is not a charge. They're not the same thing. This is the oxidation number. So in the charge, the plus or minus comes after the number, and in the oxidation number, it comes before. How do you know? Or how can you keep those two things straight? I would look at this if I got to a test, or here, and it would tell me which order they are. So if you mark it as 1+, is it wrong? It is. It is, because it's not the same thing. And we're chemists, we're not 7th graders, so we should be able to manage the difference in our minds. So I want you to be consistent with this. Also, if you just write, so in math, 1 and +1 are the same number, right? In chemistry, they're not. So if there's not a plus sign here, it also is wrong. So please just make sure that you're being very careful about the details. They're very important. Okay, so the third rule says about oxygen, it's always -2 except in peroxides where it is -1. I will tell you if you have a peroxide. What is a peroxide? H2O2 is a peroxide. What is the oxidation number of hydrogen here? +1, because it's always +1. Hydrogen's always +1, unless it's by itself, then it's 0. In this case, oxygen also is 1, it's just -1, because it's a peroxide. That's the only exception to the rule. And don't worry, I will tell you if you have a peroxide. What would be the oxidation number of the oxygen in this compound, though? In the H2O? Nope.
-1 because it's not a peroxide.
It's not a peroxide, so if it's not a peroxide, it's -2.
Okay.
Yes, we just wrote it for the other one, yep. So oxygen is almost always -2. Then there's a whole little explanation about why it is that. Don't worry about that. Just worry about that first sentence where it says oxygen is always -2. Number 4 on your red sheet says for monatomic ions. What does that word mean? Monatomic. Well, atomic means atoms, right? And what does the prefix mono mean? 1. So if you have an atom that's made out of, if you have an ion that's made out of only one ion, you have an ion of only one atom. So like Mg, and its charge is 2+. That's an ion. Something's an ion if it has a charge. Okay, so my rule says the oxidation number is equal to the charge on the ion. So if the charge is 2 plus, the oxidation number is plus 2. If your charge is 2 plus, the oxidation number is plus 2. What's the difference? The plus is in a different place. Same thing is true for the negative ions. Chlorine has a charge of -1. So what is its oxidation number? -1. So those ones aren't too tricky. You just have to pay attention to if something has a charge or not. Rule number 5 says in covalent compounds, the negative oxidation number is assigned to the most electronegative atom. Don't worry about that. 6 and 7, though, are when things get a little bit tricky. So you're going to have to put your little tiny algebra cap on, but the one that you got when you were like in 8th grade. So it's like 7th or 8th grade algebra. That's not like AAT or nothing. All right, so rule number 6 basically says if you've got a compound, all of the oxidation numbers have to add up to 0. So what does that look like? Let's see. What's a compound? KMNO4. All of the oxidation numbers in this compound have to add up to 0. Okay, so what's the oxidation number of oxygen? -2, good. All right, look on your periodic table and tell me what it is for potassium. +1. What about manganese? What does the periodic table say for that, friend? But there's a whole bunch of other choices, right? Okay, so now was where things get a little bit complicated. We know that all of the things in this compound have to add up to 0. So I'm just going to make myself a little bit of algebra. So I put the 4 in front of the oxygen because there are 4 O's. So we have to account for the fact that there are 4 O's there. So we said that potassium is a +1. We don't know manganese. But what's 4 times -2?
-8.
All right, so solve this algebraic formula for manganese. So I'm going to combine my +1 and my -8. And then I'm going to move the -7 to the other side. How will I do that? How do I get rid of this -7? Add 7. So manganese equals +7. So now, but after I do that, I need to do, with my little arrow here, I need to put it there. Do you need to show your work? No, you do not. But it might not be a bad idea to do the work. Like, you don't have to show me it, but it might not be a bad idea to do it. Okay, this is tricky, so let's do a couple more examples of rule number 6. What was your question?
Is it +7?
It is +7. Sorry, my handwriting is bad. All right, let me give you another one. Let's try calcium sulfate. Identify the oxidation numbers of all of the species in this compound. So right away I see the O, and I'm just going to slap my -2 down on there because I know that that's a thing. What is calcium's oxidation number? Does it give you any? Does your periodic table give you any help?
Yeah,
It's +2. Okay, so now let's figure out what sulfur is. calcium plus sulfur plus 4 oxygens again equals 0. Okay, so I'm just going to put my numbers in here. It's still minus 8 because we had the same thing that we had before. But now what does sulfur equal? Plus 6. So we're going to have to write that here as well. If you have big handwriting, aka you're a microcuba, you're going to have to try to slim it down a bit and be neat when you do your homework, because otherwise it's going to be, I'm going to have a hard time reading your work. How is this doing? How are we feeling on this? Thumbs up? Thumbs down? Do we need a brain break? All right, let's take a nice little brain break for, let's do an 8-minute brain break. I'm just going to pause this here. Let's do a couple more of these, and then we will do the last thing, and hopefully it'll all make some sense. Okay, what happens if we have something a little bit more complicated? Like this, for example. Rule number 6 is still true. So all of the elements, all of their oxidation numbers must add up to 0 for a compound. So what is the oxidation number of oxygen? Minus 2. What is the oxidation number of magnesium? It's plus 2. Okay, so we can still do our same algebra as before. We have only one magnesium ion or atom in this compound. How many nitrogens do we have? 2. And how many oxygen? Does that make sense? We have 2 nitrogen because of the parentheses, 6 because we multiply the 2 times the 6. Okay, so I'm going to put my numbers in. 6 times minus 12 is, I'm sorry, 6 times minus 2 is minus 12. Okay, so now I'm going to combine these two things. So I should have minus 10 equals 0. 2n equals plus 10. So what does 1n equal? Plus 5. You don't need to do all of this, but you might want to. All right, let's do something even more complicated. Okay, calcium that still has its plus 2 charge, or I'm sorry, plus 2 oxidation number. Oxygen is still minus 2. And so now when we're writing our algebra, we'll have 3 calcium. How many phosphorus? Good. And how many oxygen? And that, 8 O's, and that should add up to 0. Okay, so 3 times plus 2 is plus 6. And then 8 times minus 2 is minus 16. And so in this case, it's 5 again. Will that always be true? No. How do you know? You have to do this. You can do it in your head. Good. Good for you. Do it in your head. I don't care. I don't need to see your work anyway. So it doesn't bother me if you don't show it, because I don't need to see it. But if you need to do it, a scrap paper might be useful. How are we feeling on these? Are these okay?
Magical.
We're feeling magical, Kaden. Wow. Look at you. Okay, so the last rule is rule number 7. And it tells us that when you have a polyatomic ion, all of the oxidation numbers no longer add up to 0. They add up to whatever the charge is of that ion. So, for example, if we have NO3 minus, my oxidation numbers must add up to not 0 now, but -1. So I'm going to write N plus 3 O's equals -1. Why? Because before the charge on our compounds was always 0. And so that's how we knew to make it equal to 0. Now the charge is whatever the ion's charge is. And so it needs to equal that thing. Oxygen's oxidation number is -2, so N equals +5. Now sometimes it can be hard for us. We're smart people. We're not dumb. We can do simple math like adding negative numbers. But sometimes it can be like a kind of a mind bleep when we have to subtract a negative number, because that means you really have to add it. And so if you need to use your calculator, don't feel like there's any shame in that. Or sometimes sketching out a little number line also can be helpful. All right, let's do one more example of this, and then I'm going to send you on your way. Let's do... Let's do SO3 2-. Identify the oxidation numbers in this compound. So this is already half done. We know that oxygen is -2. See if you can figure out what S is on your own. It should all add up to -2 because that's the charge of my ion. So that means that S here should be +4. How did that go? Okay. You need to be good at this in order to do the rest of redox chemistry. So, let me give you the homework. This is due next Wednesday already. But I think that if you still have like 25 minutes here. I think that if you don't know how to, you can only do page 1 so far. You don't know how to do the other pages yet. But there's no page 4. Like usually there's a page 4, but there's no page 4 today. So that's nice. Yes, so you can do page 1, but that is all. I'll teach you how to do page